Hello students, today we will discuss about CMOS inverter, how it works. So as we see in this diagram, a CMOS inverter is made up of one P MOSFET and one N MOSFET, with both the gates are connected together at the input, and the drain terminals of both the MOSFETs are connected at the output. So the source of P MOSFET is connected to VDD and the source of N MOSFET is connected to VSS. The gate terminals are connected to V input and the drain terminals are connected to V output. So VGSN, the gate to source voltage of N MOSFET, is nothing but the input voltage, and the drain to source voltage of N MOSFET is nothing but the output voltage. The gate to source of voltage of the P MOSFET is Vin minus VDD. As we see here in the circuit diagram, the sum of the drain to source voltage of P MOSFET and drain to source voltage of N MOSFET should be equal to VDD, assuming VSS is equal to 0. So as we see here, the current that flows through P MOSFET is same as the current that flows through N MOSFET in magnitude. The direction of the P MOSFET current is from drain to source, and the direction of the N MOSFET current is from drain to source of N MOSFET. So the IDSN is equal to minus of IDSP. And if we try to analyze the working of this inverter, we expect the output versus input graph to be something like what we see here, with output being high up to input voltage VDD by 2 and output is low from then onwards. We need to prove the characteristics of CMOS inverter to follow the inverter characteristics. So if we analyze by knowing the VI characteristics of the N MOSFET and the P MOSFET, we can get the operating points and find out what is the output for a given input. As we see here in this graph, the N MOSFET characteristics for different gate to source voltage is shown, and in this quadrant you find the P MOSFET characteristic curves for different gate to source voltages. We know that the currents are in the opposite direction, but in order to analyze this in a proper manner, we need to identify the operating points. So what we can do is, we can do slight adjustments in our visualization. So we can fold this map or the curves in such a way that IDSP can be plotted on the top by showing its direction. So if we fold these curves onto the first half, we get the P MOSFET curves towards left and N MOSFET curves towards right. Then, knowing that the VDSN of the N MOSFET is the sum of VDSN and minus VDSP is equal to VDD, what we can do is, we can fold these curves onto the first quadrant. When we do that, we come to know that the curves look like this. The two curves are overlapping on the operating point. To know the operating point, we have to understand what is the input voltage of the N MOSFET and what is the corresponding input voltage of P MOSFET. When the input voltage is the least, that is threshold voltage 0.2 times of VDD for N MOSFET, the input voltage for P MOSFET is minus VDD minus 0.8 VDD. That is, if the N MOSFET curve happens to be this, the P MOSFET curve happens to be this, and the operating point meets here. So we can see here that N MOSFET is in the saturation region, P MOSFET is in the non-saturation region at this point. As we increase VGS further, you get the second curve, and corresponding curve for P MOSFET is this, and the overlapping occurs here. So you can identify the different points of operation by identifying the curves for a given input voltage. Knowing that there are there are 5 regions of operation, you can find out the output in all these 5 regions of operation. So when input is less than VTN, you get first region of operation, and when input is greater than VTN and less than VDD by 2, you get the second region of operation. When input is VDD by 2, you get third region of operation, and when input is greater than VDD by 2 but less than VDD plus VTP, you get fourth region of operation, and when input is greater than VDD plus VTP but smaller than VDD, you get fifth region of operation. As we see here, in the first region of operation, the N MOSFET is in the saturation. The N MOSFET is in the saturation, and that is for this operating point, N MOSFET is in saturation and P MOSFET is in non-saturation region. Similarly, for this operating point, P MOSFET is in the saturation and N MOSFET is in the non-saturation region. Below these points, below this, there is no current flow. So, what you can say, N MOSFET is in cutoff region and P MOSFET is in non-saturation region, as the curve is raising there for P MOSFET. And similarly, in the fifth region, that is corresponding to no current flow, P MOSFET is in the cutoff, N MOSFET is in the non-saturation region. And when input is VDD by 2, both the MOSFETs are in, that is not shown clearly in this curve. So when input is VDD by 2, both the MOSFETs are in saturation region. So we can analyze in each of these regions by writing the expressions for the current, as we know the values or the expressions for the currents in each of this region. So as we saw here, in the first region, P device is off, N device is on, that is in the non-saturation region. And in second region, N MOSFET is in saturation, P MOSFET is in non-saturation region. In third region, P MOSFET is and N MOSFET both are in saturation. And Vin is given by VDD plus VTP plus VTN into square root of beta n by beta p divided by 1 plus square root of beta n by beta p. If we make beta n by beta p equal to 1, then Vin will be found to equal to VDD by 2 when we consider VTP is minus of VTN, and that defines the center point of the transfer characteristic curves. As we increase beta n by beta p ratio, the curve moves towards left. As we decrease beta n by beta p ratio, the curve moves right side. We find that whenever there is change, that is, when input is changing from low to high, we can expect current to flow, and when input is changing from high to low, we can expect current to flow for a very short time and for short duration, and hence we can say the current only flows during transition and not during static conditions. Hence, you can say static power dissipation in CMOS is almost equal to 0 when there is no leakage. And you also see the noise margins of CMOS is quite high